Okay, so we'll do an example of kind of how the interactions between our stress and strain occur, including taking into account some Poisson ratio stuff. So say we got this system here, we've got this collar that's fitted over this shaft. The length of the shaft is 75 millimeters. The diameter of the shaft is 24.993 millimeters. And then this collar here that we have fitted onto it is 25.010 millimeters. Again, that's the diameter of the internal diameter there, the diameter of that hole. So again, going back to your fit system, that'll be a sliding fit. So we want this thing to be able to slide back and forth along the shaft relatively easily, but without interference. But let's say we do something to it. Let's say we apply some sort of force on the ends of the shaft that's going to cause deformation. So what deformation would occur would be that the shaft would get a little bit shorter and it would get a little bit fatter. And obviously, scale there is exaggerated, but eventually you're going to get to a point where it gets shorter enough and it gets fatter enough that the walls that the edges, that the sides of the shaft fill up all the space in the inside of this hole here. So we're going to get interference at some point. So we're asking here how much load can be applied before interference begins for these types of materials. We got aluminum 2014 T6, and we got structural steel A36. And again, I picked those primarily just because they're listed in the back. The material properties for those are listed in the back of your textbook. So we're asking what load can be applied. We're also asking for the stress tensor at a point in the middle when this occurs, and we're also asking, so if we kind of do this by fixing one end and then applying the force applying the load to the other, a moving load to the other, how much is that end going to move when this occurs? So are we worried about an XYZ, we're going to be working with an XYZ coordinate system? Probably not. Again, it's a cylindrical, these are cylinders, so we're probably best off working in a polar coordinate system. So again, we'll be working in a ZR theta system, where our Z's going to be, anything perpendicular to the face, so coming out of the end of the shaft. Our R is going to be, when we're looking at the face, we're looking at the side view, the R is away from the center. And then the theta, again, is just around the circles that surround the center of the shaft. So we got our sigma Z. We might call it sigma Z, we might call it sigma ZZ. Either way works, they're both equivalent. And the average stress in the middle there is going to be equal to the load divided by the area. And again, we're at the very least we're far enough from where the points that the loads are applied that the stress will have a chance to basically have averaged out. And again, depending on what the supports are like at these points, they will be averaged throughout. Basically, like if you take some flat plates that are frictionless and press on it from either side, then that'll cause the stress state to kind of be uniform throughout, because there's not going to be any frictional force on the ends that are applying any point loads different than just the overall load that's applied. But anyways, got a load divided by area, so pi divided by, since we're working with a circular cross section, pi r squared. So p divided by pi times our diameter divided by 2 millimeters and squared. So that'll give us that ends up being 490.6 millimeters squared, which we can plug into here to give us our sigma z in terms of our p. So we're also worried about because we're worried about what happens when the shaft gets fatter, we're worried about the increase in the radial size. So we're worried about the epsilon r here, the strain in the radial direction. So again, that's given by 1 over our Young's modulus times the sigma r, but that's 0, minus the Poisson's ratio times the sigma z plus the sigma theta, which again is also 0. So those all cancel out, which just gives us this here. Our sigma r is going to be minus the Poisson's ratio divided by Young's modulus times the stress in the z direction, our sigma z. So, and then we can just plug in what we solved for previously, having that in terms of the load. So, what is going to happen at contact? What is the strain that occurs while at contact? So again, our sigma is just defined as the change in the radial dimension divided by the original radial dimension. So that's just going to be equal to this. Yes, I know that these are diameters, not radii, but again, essentially, if we wanted to convert those to radiuses, we would just take this top number divided by 2, take this number divided by 2. The 2's would cancel out, so it kind of doesn't really matter. So yeah, we got the original diameter of the shaft, and we got the diameter of the hole minus the original diameter of the shaft up top here. So that gives us a strain where the where the walls touch, basically, at 6.802 times 10 to the negative 4. And if you want to assign units to that, that's millimeters per millimeter. But that's what we're going for. That's when we get kind of our failure, our touching condition here. So we've got that. We take this that we solved for here, drag it over here, and then we're able to basically just solve for P by multiplying the area here times the strain, and then dividing by our negative Poisson's ratio, dividing by our negative Poisson's ratio, and multiplying by our Young's modulus to solve for P in terms of this strain and these two material properties. Oh, sorry, this not this strain. This strain times the cross-sectional area and our two material properties here. So let's have a look at steel first. So the steel, we've got a Young's modulus. Steel's got a relatively high Young's modulus at 200 gigapascals, and its Poisson's ratio is about smack dab in the middle for metals, 0.32. So plugging those values in, we can solve for P. So we got negative 200 GPa over 0.32 times our 0.3337 millimeters squared. One thing that I find it easy to do is just keeping in mind that a megapascal is a Newton divided by a millimeter squared. So I just convert the GPa to MPa by multiplying by 1,000, and then when I do that, the MPa times the millimeter squares cancels out to newtons. So multiplying this out gives us this in kilonewtons. Again, I divided by 1,000 to make the number reasonable. So that is a negative value because it's going to be in compression. So I got that. So we also want to, we got the value for the force we need. That allows us to solve for the stress state. So the stress state is just going to be that load. The stress state is just going to be that load divided by the cross-sectional area, which gives us 429.3 MPa. Again, this is really high. That's a very high value. In fact, if you check your textbook, I'll drag this over here, and we can zoom in a little bit. So structural steel here. Actually, here, let's rotate. I can't rotate this, can I? Yes. Okay. Okay, so we got a structural steel. Our structural steel here, and we got our Poisson. Yeah, so here's where I got our Young's modulus. Here's where I got our Poisson's ratio. If you check, you see that that value is actually going to be above the ultimate strength of the steel in question. So essentially, what I'm saying here is if we try to do this, it's going to fail before we get to that point. So it would have a stress state of this. Our sigma zr theta. I put when I'm working in the in polar coordinates, I like to put which order they're in underneath the sigma here, because when you're working with x, y, z, everyone knows that it's x, y, z. Whereas polar coordinates, people aren't quite as used to doing that. So I like to work in. I like to state it directly, which is which. Some people choose different ones that kind of go in which position as well. So, anyways, that's about that for the steel. I know it also asked for the how much the end of the shaft would move if the load is applied, but well, it's going to fail, so it's going to be a lot more than that. It's actually going to just keep squeezing, so we're no longer working with elastic, with an elastic condition, so that question kind of becomes not all that relevant. So moving on to our aluminum. So again, we've still got this relationship here that defines our load in terms of the conditions and our the material properties. So again, for Poisson's ratio for aluminum is 0.35, and it's got a lower Young's modulus. So it's a less stiff material. So its Young's modulus is 73.1 GPa as opposed to the steel that we were working with. That its Young's modulus was 200 GPa. So take those values, plug that into that equation, and that basically allows us to solve for P. So again, I did my whole GPa to MPa conversion here, and that gives us 69,695 newtons. So to get our stress state, we take that 69.7 kilonewtons divided by our area, and again, just keeping your units in mind and canceling out properly, it's newtons per millimeter that gives us MPa. So if we take this, multiply it by 1,000, and then divide it by this value when we're doing our calculations, we get our minus 421, minus 142.1 MPa. So again, still fairly high value, but it'll take the load. We look back at our values for aluminum here. Its ultimate strength is it's far above the ultimate strength. It's even far above the yield strength. It's able to hold a compressive load of 414 MPa, megapascals. So we're not really in any danger of failing in this situation, as opposed to the steel. The steel is far stiffer than the aluminum, so as a result, it deforms a lot less when loads are applied. So it gets to a failure load before it flexes enough for this, before it stretches enough for this to happen. So yeah, and then just in a tensor state, here's our sigma. Again, negative values because we are. Oh, I forgot to put a negative value on this one, didn't I? My bad. That's terrible for me. So the steel, yeah, negative 429 MPa. For the aluminum, negative 142 MPa. As for the change in length, so again, I've got the formula here for our EZ, and that'll just be when we know that this is 0 and this is 0, that just cancels out to our sigma z over our Young's modulus, and that'll give us negative 0.00194 as our strain. So that's going to be our delta L over L. So delta L is going to be equal to L times that, which means our delta L is going to be that times 75 millimeters, which means that when we apply a load, once we get to the point where we have squeezed that aluminum shaft 0.146 millimeters shorter, then it is going to get to a point where the collar on that shaft isn't able to slide anymore because it's started. It doesn't have any. It doesn't have any room at all. It's no longer. The walls are starting to interfere. So yeah, that is that.